Chapter 3 is all about determinants. And so what we're going to do is we're going to start in section 3.1 with an introduction to determinants. Now, most of this section is going to be focused on how to calculate the determinants of any square matrix. All right. So just as a remind you, we've actually looked at determinants before, way back when we looked at invertible matrices. We said that the determinant of a 2 by 2 matrix was AD minus BC. All right. So that was take the main diagonal, multiply those, then subtract the what we call off diagonal. So AD minus BC. Now, we're going to try to generalize this pattern. And so what I want you to understand is how AD minus BC came about. So just think about row reducing the matrix A into some sort of a row reduced form. Doesn't have to be row reduced echelon. Let's just take some row echelon form. So what you would do is you'd start with matrix A, and then an easy way to do this is to multiply the bottom row by A, by lowercase a here. If I multiply that bottom row by lowercase a, you come up with this matrix here. Now, how do we get rid of this AC here? Well, we multiply the top row by C. Maybe I should write down this. So what I'm going to do, multiply this by the letter A, multiply this one by C. So multiply that top row by C, add it to the bottom row, and then replace the bottom row. So I'm going to get A times C minus AC, or I should say, I should multiply that by a negative C. I'm sorry. Let me multiply that by a negative C. Okay, so negative C times A, add that, you end up with 0. Negative C times B, add that, you're going to get AD minus B times C. So notice that a row echelon form of A, we'd end up with a 0 in the 2, 1 entry, and then this AD minus BC. Now, what do we know about matrix A? If it's invertible, then it's going to row reduce to the identity. So if it's invertible, this thing is going to be non-zero. If you cannot find an inverse, then this term here will be 0. All right. So we're going to take that approach, and I'm not going to go through every single detail, but it turns out that you can find determinants by using this row reduction technique over and over and over and over again. It gets a little bit cumbersome, so we're going to transition to submatrices and talk about submatrices. All right, so imagine I have a matrix capital A. We're going to look at A sub ij. Basically, that's going to be the submatrix of A created by eliminating row I and eliminating column J of the matrix. So A sub ij, we look at the ith row and the jth column, and we get rid of them. So let's take A sub 1, 1. So if I start with matrix A and I eliminate row 1, and then I eliminate column 1, what I'm left with is this 2 by 2 matrix, which is A sub 1, 1. All right, notice that the 1, 1 entry kind of was eliminated twice. That's fine. We're left with this 2 by 2 submatrix here. I want you to go ahead and find a sub 1, 2, and find a sub 1, 3. Push pause on the video and do that. All right, hopefully you went ahead and did that. So here's basically it. So the idea is that if we're going to eliminate row 1 and column 2, row 1, column 2, the only thing we're left with is A21, A31, A23, A33. All right? And then if we want to eliminate row 1 and column 3, I'm left with A21, A22, A31, A32. Now, one thing I wanted to mention here, this is especially important in this A12 matrix, is that if you eliminate row 1 and column 2, notice that my new submatrix, the order still starts with the upper leftmost value and then moves to the right and then goes down 1. So in other words, you're not going to start this matrix with A23. We're starting with the upper leftmost value and basically taking out everything else. Okay, so when you eliminate rows and columns, you're always going to do that, no matter what. And by the way, you can do this no matter which row and which column you picked. You could eliminate row 3 and column 2 if you wanted to. All right, or any row and column you choose. Now, why submatrices are nice is because they are connected to determinants. Let's take my standard 2 by 2 matrix, and we're going to find submatrix A11, submatrix A12, and then we're going to find submatrix A21 and submatrix A22. In fact, just push pause, go ahead and do that. It shouldn't take you more than a couple of seconds. So let's do the first pair first. Okay, the A11, A12. All right, so A11, eliminate row 1, column 1. You're just left with the D. And by the way, this submatrix would be a 1 by 1 matrix. Notice that A12, eliminating row 1 and column 2, would leave you with C. Now here's what I want you to notice, and here's the big alert. The 1, 1 entry of our matrix was the letter A. If I multiply that times the number in my submatrix A11, I get a D. The 1, 2 entry in my original matrix was the letter B. And if I multiply that times the 1, 2 submatrix, I get C. Notice that all I have to do is put a subtract in there, and all of a sudden my determinant shows up as the 1, 1 entry multiplied times this submatrix element minus the 1, 2 entry multiplied times this submatrix element. Now let's do that for the second row as well. If we did that for the second row, A21 and A22. Okay, so if I eliminate row 2, column 1, I end up with a B. If I eliminate row 2 and column 2, I end up with just an A. Now again, notice something. In this case, we started with the A21, that's the B. If I multiply that times the 2, 1 entry, so B, now I'm going to multiply that by C. So BC, and then what's the 2, 2 entry? Well, it's D multiplied by the submatrix element. So we just get A times D. Now, if we just put a plus in between them and a negative on the BC, all of a sudden we get a determinant. So what's happening here is that determinants are showing up by sort of a row expansion using submatrices. And it turns out this can always be done. So if I wanted to go and find a determinant of a 3 by 3 matrix, what I could do is I could isolate one row. Now here I isolated the top row, A11, A12, A13. And then I could take the element A11, multiply it times the determinant of the submatrix when you eliminate row 1 and column 1. And then you can take A12 and then multiply that times the determinant of the submatrix when you cancel out row 1 and column 2. And then take A13 and multiply times the determinant of the submatrix when you eliminate row 1 and column 3. Now you do all three of these calculations separately, and then what you do is you'll put a positive on this A11 entry times its determinant of the submatrix. You'll put a negative on the A12 times the determinant of the submatrix, and you'll put a positive on A13 times the determinant of that submatrix. Now, in our example before, notice that sometimes we had to use a positive on one and a negative on the other. Here we're using a negative on one, a positive on two others. Well, that negative positive has a pattern. In general, if I want to find the determinant of A, what I do is I expand out on some row. Now it actually turns out that it doesn't always have to be this first row. I could have expanded on the second row. I could have expanded on the third row. I could have taken this A31, A32, A33, and did the exact same thing with the submatrices. And you could find out also, I didn't do this in the last example, but if you were to go back to the last example, you could have also expanded using the columns. So I could have done A11, A21, A31 times the determinants of their submatrices. So any row or any column you can expand out on. But what you do is you take the entry times the determinant of the submatrix. And then whether or not it has a negative depends on which row and column we were in. So notice that in our examples, when I dealt with A sub 1, 1, that was going to be a positive entry because 1 plus 1 is 2. So negative 1 to an even power is going to give you a positive coefficient. And whenever our I plus j added to an odd number, like in A12, we had to make it a negative out front. So we just pick a row or pick a column and expand out using this formula. And again, the negative versus positive depends on whether the subscripts add to an even number. If those subscripts add to an even number, then it's going to be a positive coefficient. If they add to an odd number, it's going to be a negative coefficient. Or then I should say negative out in front of whatever the coefficient is. All right, and this says for a specific I. That just means we can do it, we focus on one row at a time or one column at a time. Okay? All right, so let's go ahead and do an example. All right? If you want, if you feel comfortable, push pause. Otherwise, we'll do this in about 5 seconds. All right, so I am going to go and click on a Word document, and we're going to expand. Now, again, it doesn't matter which row you pick, or which column you pick. Um, I'll do the first row just because we've dealt with that, or that was our original look. So I'm going to deal with the first row. Now the first entry here is a 4. 4 times the determinant of, well, the submatrix, sorry, the submatrix that you're going to get. I'm going to try to do this quickly as I can, is going to be 3, 2, 0, 4. 3, 2, 0, 4. Okay, again, one way to say is the number 4 is in row 1, column 1, so eliminate that. Another way to think of it is anytime we start expanding on a row, what I'm going to do is I'm going to take that element, I'm going to get rid of the row that it's in, I'm going to get rid of the column that it's in, and I'm going to look at the rest of it. Now, so it's going to be 4 times the determinant of this 2 by 2 matrix. Now, the reason why 4 is positive, because 4 is the 1, 1 entry. 1 and 1 add to 2, which makes it an even number. So we're going to get a plus 4 right there. Now the next one we have to deal with is this 1. So we're going to take 1 multiplied times the determinant of the submatrix. Whoops. So times the submatrix, if we eliminate the row and column that 1 is in, so row, eliminate, columns in, I'm going to get negative 1, 2, 7, 4. Now, since 1 is in the row 1, column 2, 1 plus 2 adds to 3, that means I'm going to get a minus out in front of here. So we got, whoops, 4 times the determinant of that submatrix minus 1 times the determinant of that submatrix. And then lastly, the 6. Well, let's take care of this. This is in row 1, column 3. 1 plus 3 is even, so you're going to get a plus 6 times the determinant of the submatrix that we're looking for. Now, the submatrix in this case, whoops, is going to be, if I eliminate column 3 and row 1, I'm left with negative 1, 3, 7, 0. And therefore I can, let's try to expand this just a bit. I don't know if that's going to work or not, but yeah, we'll see if it works. So we'll expand that just a bit. So 4 times this determinant minus 1 times this determinant plus 6 times this determinant. And why that's nice is because we know how to calculate the determinant of a 2 by 2 matrix. So we're going to take 4 times, this is going to be 12 minus 2, or excuse me, 12 minus 0. Hopefully everybody remembers how to do a determinant of a 2 by 2. 3 times 4 minus 0 times 2. Then minus 1. Well, determinant of this is going to be negative 4 minus 14 plus 6. Well, determinant of this is going to be 0 minus 21. All right. So we end up with 4 multiplied times 12 minus 1 multiplied times a negative 18 plus 6 multiplied times a negative 21. Okay, you can type that into your calculator. It's a pretty big number, but it's pretty large, cumbersome determinant, but it is just, that's the determinant. So in short, the determinant is a negative 60. So I believe, again, unless I've done a silly calculation mistake, I think I get a negative 60 as my determinant. Okay, so that's how we can find the determinant of a general 3 by 3 matrix. And by the way, now that we know how to find the determinant of a 3 by 3 matrix, we can define the determinant of a 4 by 4 matrix and a 5 by 5 matrix doing the same thing. Now there's going to be a lot more expansion and things of that nature, but it's the same concept. You just keep getting down to submatrices until you can get the 2 by 2 case, and then hopefully that makes your life a little bit easier. So what I'd like you to do is push pause on the video, try this one, and I'm going to give you a little hint. Notice that third row has 2 zeros in it. So using the third row expansion will be fairly nice. So go ahead and push pause on the video and try this one. Right, so hopefully you went ahead and did that. Again, the third row is going to be probably the easiest to expand upon because of zeros. When we find determinants, it's really nice to have zeros, to be expanding on rows with zeros. So let's go ahead and do that. So if I take this third row and I expand, well, 0 is the 3, 1 entry. 3 plus 1 is 4, that's even, so I'm going to get a positive. Not that it matters on 0, but it's going to get a positive 0 times the determinant of the submatrix. Again, when you eliminate the first column and the third row, eliminate this 0 spot is what I'm looking at here, we get the submatrix 3, 1, 2, 5. All right, so 0 times the determinant of that. And then I look at 1. 1 is the third row, second column. 3 plus 2 is 5. So I'm going to get a negative, a minus 1, times the determinant of its submatrix. Again, in order to find the submatrix, eliminate the row and the column that the number 1 is in. So we get negative 8, 1, 6, 5. And then the last entry here is 0. And we're going to eliminate it. First off, it is the third row, third column spot. So row 3, column 3, that adds to 6. So that's even. So you're going to get a plus 0. Again, not that it matters on 0, but just in general. Eliminate the column and then the row that 0's in. And we get the submatrix negative 8, 3, 6, 2. Now, notice that this is really nice to deal with. Okay, in particular, this is nice to deal with because this first whole thing, 0 times the determinant, I really don't even need to know that the determinant of this is going to be, what is that, 15 minus 2, so 13. It doesn't matter that the determinant of this is 13 because it's all going to end up as 0 anyways. So I'm going to get 0, this whole thing, minus 1. Now this one I do have to calculate the determinant. Negative 8 times 5 is a negative 40. Then we're going to do minus 6 times 1. So negative 40 minus 6. There we go. And then lastly, we get a plus 0. Again, I don't even care what the determinant of this is. 0 times anything is 0. So there we are. All right. What you'll do is you'll see that this is going to be a -1 times -46. So the determinant of this matrix is simply 46. Okay. So when you end up with zeros, it turns out to be really nice. Now that same rule for submatrices is going to work no matter what size matrix we deal with, okay? I will say this, we're only going to, determinants, we're only going to be concerned about determinants. They're really only worth calculating if we end up with a square matrix. So everything that I'm going to give you is going to be square. But this definition is going to be true no matter what size I have. So what I'd like you to do is look at this 4 by 4 matrix. This is probably about as big as we'd go to. And try to calculate the determinant of this matrix using a row expansion or a column expansion. I think what I would do probably is I would start and I would expand along this last row here. Okay, so try expanding on the last row and see what you get. Okay, hopefully you went ahead and did that and saw that this is a fairly involved process, but it's better the more zeros we have, right? So the more zeros we have, the easier our life is going to be. All right, so what I did is I expanded on this fourth row because it had a couple of zeros in it. You could have also chose the second column that also has a couple of zeros in it. But again, more zeros makes our life a little bit nicer. So here's what would have happened. We've taken this, again, I chose the fourth row. Now, notice here, this 0 here is in row 4, column 1. 4 plus 1 is 5, so I would have to put a minus 0 times the submatrix that we get when we eliminate the first row, or excuse me, the first column and the fourth row. So I don't even care what that submatrix is. I'm not even going to write it down. I know it's this right here, but I don't even need to write it down because I know 0 times anything is going to be 0. Now, the next thing we do, we go 6, and again, 6 is in the second column and the fourth row. 4 plus 2 is 6. Even number means I'm going to use a plus 6. So plus 6 times the determinant. If we eliminate this column and the fourth row, we end up with 2, 8, 0, negative 2, 4, 2, 1, 3, 1. All right. And then you just kind of keep going back and forth. By the way, notice that this is always going to go negative to positive to negative to positive, or it'll start as positive, then go negative, then go positive, then go negative. When we expand on 0, 0 times the determinant of getting rid of the fourth row and the third column, whatever that's going to be, it's going to give us 0. And then I'm going to expand 3. If I get rid of the fourth row and the fourth column, we're going to be left with 248, negative 204, 103. Okay? Now, at this point, what we would normally do is we would take this whole thing and say, well, let's get rid of the parts which are 0. I know that part's going to be 0. I know this part's going to be 0. And so we'll be left with, oops, excuse me, we'll be left with this. Okay? And then what we would have to do is find the determinant of this matrix individually, and then find the determinant of that matrix individually as well. And again, this one's going to be taking a little bit of time. So let's scroll down a little bit. Let's make some room for ourselves. Let's find the determinant of that matrix. Once we've done this a few times, hopefully we can figure this out. So what I'm going to do is I'm going to use the third column because it has a 0, 2, and a 1 in it. So 0 times the determinant of the submatrix. I guess I'll write it down even though it doesn't matter. By the way, this is in the first row, third column, so that's going to be a plus 0 times the submatrix negative 2, 4, 1, 3. By the way, if you expanded along the first row, you'd have been just fine. That'll be a minus 2, again, third row, second row, third column, times the determinant of, what's that submatrix going to be? That submatrix is going to be, I'm kind of being quick about this, but 2, 8, 1, 3 plus 1 times the determinant of this submatrix. What's this submatrix going to be? Well, it's going to be 2, 8, negative 4, negative 2, 4. 2, 8, negative 2, 4. Okay. Now that is going to be 0 minus 2 times 6 minus 8 plus 1 multiplied times 8 plus 16. All right, you can calculate that for yourself if you want to do that. So all of that to just figure out the determinant of that 3 by 3 matrix is going to be, let me calculate this. So negative 2 multiplied times negative 2 plus 1 times 24, we end up with 28. So determinant of that 3 by 3 matrix is 28. Whew, that was a long. So what we can do is we can go up here, back to the original, and say, well, this is actually going to be, whoops, where are we at? All right, this is actually going to be 6 multiplied times 28. Again, 6 times 28 plus 3 times, well, now I got to go find the determinant of this guy. Determinant of that guy, we can find that fairly quickly because that guy's pretty nice. I'm going to go on the side here. We can do a, well, let's do a column expansion on column number 2. So we're going to do 4 times the determinant of submatrix. I know I'm forgetting the brackets every time, but that's times the submatrix negative 2, 4, 1, 3. By the way, this 4 is in row 1, column 2, so we're going to put a negative on the front of that. Then I take the next element in the second column, which is a 0. It's in the 2, 2 spot, so it's going to have a positive. Then you're going to do times the determinant of the submatrix. Now again, this one we don't even have to write if we don't want to, but I will, just for sake of being thorough. Sorry about that. So eliminate row column, you get 2, 8, 1, 3. All right, and then my last element, minus 0 times the determinant of, again, that's a minus because it's in row 3, column 2. So times the determinant of the right submatrix here. So if I eliminate row 3 and eliminate column 2, I get 2, 8, negative 2, 4. All right. Again, this one's one of those nice ones in that 0 shows up twice. So we're ending up with negative 4 times, this will be negative 6 minus 4 plus 0 minus 0. All right. So negative 4 times a negative 10 gives us a 40. Uh-oh. All right, hopefully you've caught that. Negative 4, this becomes negative 10. So negative 4 times negative 10 is 40. The zeros aren't going to do anything. You can just erase those if you want. And there you go. Now, all of that was just to get the fact that 40 is the determinant of this matrix. 28 is the determinant of that matrix. So if we wanted to go back up and finish our problem off, we would say, well, this 4 by 4, we know it's going to be 6 times the determinant of this, so 6 times 28, plus 3 times the determinant of that matrix, which is 40. And so the determinant of that 4 by 4 matrix is whatever we get when we take 6 times 28 plus 3 times 40. And I got that the determinant of the matrix is 288. Whew. Now, a couple things I want to mention before I move on, okay? First off, if I was doing this if I were going to ask you to do this on a test, I probably wouldn't go all the way out to the 4 by 4 case. I'd probably do a 3 by 3 case and ask you to expand using one of the rows or one of the columns. Okay, but I will ask you to do this by hand at least once on the test. Okay, but I do want to say we got 288. And we could have tried to use our calculator as well to get that determinant. All right. In fact, this is a fairly good check. So go to your calculator. If you're not there yet, just push pause and go to it. And then obviously we're going to input the matrix A. We're going to edit that. We're going to let matrix A be our 4 by 4 matrix that we dealt with. So if you remember, again, you can go push pause, go back on the video and check that out. But it's 2, 4, 8, 0, negative 2, 0, 4, 2, 1, 0, 3, 1, and 0, 6, 0, 3. Okay, so put in matrix, again, we usually use A, but any matrix slot would have been fine. And then go back to the matrix menu in math and notice that the very first entry here is determinant. So DET, determinant, hit enter. Determinant of matrix A, sure enough, is 288. It's the exact same number we found because, again, well, we found it correctly, I guess. That's a good check. All right. So when you're actually calculating determinants, you can always go and check on your calculator to see that you've calculated it right. And in fact, go ahead and check on the calculator in our previous problem as well. Okay. okay? You could put this one in the calculator, you could have put that one in the calculator and seen what the determinants were. All right. Now, you can put this one in the calculator if you'd like, or you could expand. But I want you to go ahead and find the determinant of this matrix. In fact, let's say this. I want you to find the determinant of this matrix both by putting it into the calculator and by using a row expansion or a column expansion. Okay? When I do my column expansion, I'm going to do it on column 1. So I'm going to start using negative 11, 0, 0. So I'll do column 1, but you could have used anything. So go ahead and push pause, find the determinant, use your calculator to do it, and then check that you got the same answer when you expand using, I'm going to use column 1, you could use whatever else you want. All right, so hopefully you went ahead and did that. Now, when I use my calculator to do that, what I get is the number negative 539. Now, let's see how that came to be. So we go to the Word document. Again, I'm going to use the first column in expansion, negative 11. Now, the submatrix, when I get rid of row 1 and column 1, the submatrix is 7607. And then I'm going to expand using this row, or excuse me, this column here. So I'm going to go my second entry in the first column. By the way, second entry in the first column, technically you'd have a negative 0. Notice I had a plus negative 11, so I kept it as negative 11 there. Times the determinant of its submatrix, that's not going to matter a whole lot. And then this other 0 times the determinant of its submatrix, that's not going to matter a whole lot. So basically all you're going to do is you're going to wind up getting negative 11 times the determinant of this submatrix here, 7607. Now notice what's going to happen here. We get negative 11 multiplied times 7 times 7 minus 0 times 6. Minus 0 we don't even have to write. So what did we get? We got negative 11 times 7 times 7. And sure enough, that gives me that number I said, negative 539. Okay? Now here's what to take away from this example. Negative 11 times 7 times 7. Those are just my diagonal entries. And this was a special matrix because what kind of a matrix was this? This was what we call an upper triangular matrix. Hopefully you remember that from dealing with upper triangular matrices in the last chapter. So this was an upper triangular matrix, and you can convince yourself that anytime you have a triangular matrix, whether it's an upper triangular or a lower triangular, the determinant is always going to be just a product of the diagonal entries. Because you start row expanding, you do a column 1, you only end up with negative 11 times the determinant of this submatrix. And then if you're going to find the determinant of a submatrix, again, it'd be 7 times the determinant of its submatrix, and then zeros would go away. So you're going to end up always with just a multiplication of the diagonal entries. Again, don't forget that's only if your matrix is triangular. And that's what the next slide says. The next slide says that if you have a triangular matrix, again, a square triangular matrix, we're not going to deal with anything that's not square in this section, then the determinant of A is just the product of the diagonal entries. Now this is going to save a lot of time finding determinants, right? Even plugging a 4x4 into our calculator can be fairly cumbersome, or a 3x3 into our calculator can be fairly cumbersome. A lot more than just taking a product of, for instance, -11 times 7 times 7. So I want you to just quickly find the determinant of this matrix. Push pause on the video and see how it goes. All right, hopefully you went ahead and did that. The determinant of this matrix is simply -60. We notice that it is a triangular matrix. In this case, it's lower triangular. So it's lower triangular, but it's still the same. I could have expanded along row 1, got a bunch of zeros, ended up with 10 times this. So it's triangular. We look at the diagonal entries. 10 times 6 is 60, times -1 is -60. So the determinant of this matrix is -60. And notice how much time that's going to save us on a 4x4. We can simply look at this 4x4 matrix. We can say, well, this is lower triangular. So 4 times -2 times 3 times 5 becomes -120. So I know that the determinant of that matrix, without having to do a lot of calculation, is -120. So -120 is the determinant. Now, I do want to introduce just a slightly different notation that you're going to see in the book, you may see in the homework, and so on and so forth. So what I've been doing so far, whenever I calculate determinants, I wrote DET and then in parentheses the matrix. Sometimes I was a little bit fast and loose with my notation and didn't write the brackets, but I wrote DET in parentheses the matrix. Well, you can also use like this absolute value notation. So you just put, instead of those brackets, you put absolute values around the array. So again, determinant of the matrix is the same thing as putting absolute value around the array. Now these aren't actually absolute values, but they're just another way to write determinant without having to write DET. So sometimes people like to use that because it goes a little bit quicker, takes a little bit shorter time to write that, takes a little bit less space on the paper when you're writing it. By the way, this determinant, this is 2 by 2, so 3 by 3 is 9 minus 8. So the determinant of that matrix is 1. So I'd like you to do just a couple of these really quickly. It shouldn't take you very long, but I wanted to make sure that we were aware of this new notation. So calculate the determinant of the following two matrices and do it, by hand as quickly as possible. All right, there we go. All right, so hopefully you went ahead and did that. We're going to take 7 times 4, get a 28 there, minus 8 times 2, so minus 16. So let me actually go to a Word document so it makes sense a little bit more. So 7 times 4, 28, minus 16, which gives you a 12. All right, so the notation would be this. Again, determinant of this matrix is 12. Again, using these absolute value signs is equivalent to asking for the determinant. And then we go to the next one. Well, the next one we see is upper triangular. So all we have to do is multiply the diagonal entries. -5 times 4 times -6. Well, that gives me 120 as well. So 120 is the determinant of that matrix. So the notation would be exactly what I wrote there. So hopefully you get the idea of calculating determinants and figuring those things out. Again, on the test, I will ask you at least one time to do a row expansion of like a 3 by 3 case, and then you should know how to figure out determinants on the higher cases. I probably won't ask you something as cumbersome as this example was, this 4 by 4 example on the test, but just know that we can do it. All right. And if you're ever stuck, always, again, that there's a determinant button on our calculator, so you can always check your work using that. All right, well, that is the end of section 3.1. And so we'll get into 3.2. We'll get into using these determinants in the next section.